So just quick introduction on these slides. I hope I can go through this with you in more detail. So my name is Kevin Xu. I'm from Intel Corporation, to be detailed in data center group, which is more supporting the cloud customers specifically on their product enabling. To be more is on Xeon and the persistent memory product in the future, right? So I have some colleagues like Peifeng Si and Jiming Li, who's also my colleague working on this project, but unfortunately they cannot be able to join. So I would just appreciate them in advance to be here, right? So this is the agenda I'm gonna have for today. Introduce how the persistent memory is, and then some of the general challenge were met during enabling for the customer side. And to be more specific, Redis is the one I put in the title there, of course. This is the first one enabling for the customer side, and we also make it open source, with our customization part. And you will see what I introduced, a scenario for Redis it can come into, and then introduce what the PMEM can be used to, to introduce the performance and the capacity part for the Redis one, right? Two scenarios over there, and then I'll introduce to make the feature more complex and completed to be able to put in production. What other features we need to consider about to make it ready for redeployment. All right, and the last one is summary what the this kind of work needs to be done. So talking about the persistent memory technology, it is we call it many ways. The title original to be there is NVM, but to be more specific, I put it is the persistent memory, just comparing to what the flash as the memory side. The Redis lab has once released a version called the Redis on flash. To be more specific, this is the one on persistent memory, which is going to on the 3D XPoint technology adopted by Intel, and to be product going to be the DC PMEM product in the future. This is the more specific version talking to on that, right? And this is the hierarchy what the 3D XPoint can locate to, and comparing to what the NVDIMM locates is kind of bigger capacity and the somehow a little bit slower than DRAM, but much more less latency and the high performance than traditional NVMe SSD. So that's why the hierarchy locates for this kind of the product. And the character it has, just like mentioned before, it has a very large capacity compared to what the traditional DRAM has, and on that against you, so it has lower dollars per gigabytes for sure, right? And then to be more on performance side, we try to pitch that to be close to DRAM throughput and the latency has, and persistency. This is the user's option to make the persistency capability of the, this kind of the persistent memory or not during the workload enabling. All right, so when we meet with the persistent memory, we have this kind of the enabling challenge when we meet before. When it's a kind of layer jumping into the whole storage layer, we found it has a lot of work to do with computer architecture. It has what kind of the DRAM it needs to be played with, and it needs to support additional persistent memory protocol. It needs to have the memory controlling CPU side to support that, and to use this kind of the device, should we treat that as the the DRAM as the hierarchy level, or treat that at the same tier as the DRAM, right? There are different ways to use this kind of the device. So this is regarding more to enabling the computer microarchitecture to support that. And secondly, is the ecosystem enabling and the OS support. To have the OS support, it has a lot of ways to say how to better optimize the memory management and the lower cost for those kind of memory management capability with less fragmentation, actually like that, right? So this is also the other way to enable all kind of OS to support. And we have a lot of sessions in these 3 days, conference talking about program model, right? The PMDK, the program model for the persistent memory. There are a lot of sessions talking about that. So this is also what we need to consider to introduce the end user how to correctly program the the application to fit the right model, what kind of the raw device you should mount, or block device, or file system you should use. So these kind of options provide a lot of the choices for customer to enable. And the last one is the data management strategy and implementation we're gonna have for real workload logic itself. So next session, probably I will introduce more on data management strategy and implementation to say in a real workload, right, particularly one by one, what kind, according to its logic and its character, what kind of data management strategy we could have to increase the performance at the best level. All right, so coming to Redis itself, I suppose is everyone here understand about Redis, or actually work on Redis there, right? I hope so. But this is the Redis Introduction, right? It is very popular open source in-memory database. It has been widely deployed by the cloud service provider for the cache for different kind of the services for a lot. It has offered the high performance compared to what the RMDB or traditional non-SQL database which leverage the SSD. It has the unique data model with the option durability as well. So user can choose what kind of durability they want to have for the Redis enabling. For the major data type, it has 5 major data types so far, which is the string, list, hash set, and z set for different kind of the real scenarios, right? You can cover like what needs to be the time series one, and how the message queue can be used for producer and consumer, and what the label can be used for, like the bunch of the data set can have different kind of label to that. And social network, right? Everyone use the Facebook. The social network can also be used as the high performance to store relationship in this kind of the database, and ranking, right? Like top 10, what kind of top 10 or top 100 user rating that is. This all kind of scenarios can leverage Redis as the use case. And to the picture in the left side, it enables to say how the user enable the traditional durability for data in the Redis itself. To say the Redis itself has the mechanism to log every operation into one file, which is called the append only file. And this file is to store and replay any kind of the operation to keep the data back to normal when the server crash, right, or after server crash, right? So this is what the current durability mechanism Redis built up, and this is stored in the disk itself, right? And there's other way like RBD, which is like the snapshot for the Redis database itself. I didn't highly mention about that, but there's other introduction to say how we work on this kind of mechanism itself to improve the best performance. All right, so talking about Redis management strategy on PMEM, to keep it very simple, we pick up the strategy like this, right? To say, because there's performance delta between DRAM, DDR4 and PMEM. So how we recognize those kind of performance delta, and by the chance for the data pattern itself, how we do that. So to put that in this way, we put the simple strategy to say when a value is bigger than the threshold we set, or user can set themselves, should move to PMEM itself. And the keys, which is small, usually small, and operate a lot, were kept in the DRAM. The more detailed, the keys kept in DRAM, including all the key value metadata management and user operation relevant to those metadata management. So those kind of the small stuff were kept in the high performance DRAM, while keep the large data or large value into the PMEM. So that's the general concept for this kind of the data management. And for different kind of usage like volatile, non-volatile, I'll introduce more comprehensive way in non-volatile mode. Right? So 2 scenarios. The first one, use the PMEM to increase the Redis instance capacity. So this is why people like to use the PMEM a lot, because it can save a lot of the additional density for the capacity itself, right? To the service provider, cloud service provider, this is the revenue coming, where they can spawn more revenue coming from the more instances of the same service level of the SLA provided by Redis. So to be more specific, there are several ways to modify in that case. The first approach, we can see to store all the heap data in the PMEM. This is very straightforward way to do that. And this is how we think the PMEM can be used in the gut feeling, right? Normally, because Redis use the JMalloc on the memory management, the most straightforward way is to use the persistent memory malloc in the similar way, which has minimal code change to current Redis itself, right? So here we use the libmemcon, which is going to be included in the PMDIC itself to do that way, right? And the right picture describes how the test environment is set up, and like to say we simulate the environment to stress the workload from the Ethernet, and use the different kind of the high core skill to every core has one instance spawn, and using that kind of setup to stress the Redis workload and get a performance like that, right? So you'll see in this kind of way, the performance is not as expected as the end user demands. So that's reality we have to face so far, right? The marketing team in Intel, by the way, the marketing team in Intel prevented me to show any performance data, so I cannot show you what exactly it has, but I can show you the logic, how we modify that, all right? So yes, the option 1, you see this kind of approach, store all heap data in PMEM, it has a lot of the performance optimization opportunity can be found there, right? The big and sequential data access pattern has better performance, in the PMEM than a smaller and random access. This is, everybody should know that, right? And how to recognize this kind of opportunity and adopt that in the code modification is the way we need to do. And meanwhile, in Redis, we characterize the status for what the data pattern, access pattern for that. Found a lot of the management data structures are actually very small and usually accessed randomly. So that's why we found we should probably have better data management principle according to that, right? So here comes the second option, design option, to see we not store all the heap data into the PMEM, but store only the large heap data in the PMEM, right? So here we set the threshold at default like 64 bytes by default to say what the data bigger than 64 bytes should move to DRAM, and the rest of them should move to DDR. And so that's the general logic as I mentioned before, right? So with this kind of modification, we can get the performance close to Redis performance on DRAM itself, right? So this can be easy change according to better data management the benefits can bring by. And I introduced several key changes. If you are not this software developer, goes to the Redis source code, you probably can just understand how logic it is, right? So in the table, as I just mentioned about, there are five big data types in the Redis itself. I'll introduce one by one quickly, but the chart here means what the detailed encoding each type has, and what the location we recommend on the better data management locates, right? So you'll see each string, the raw data sometimes will be bigger. So if the bigger than the threshold, we put that in the PMEM, while putting the SDS pointer in the make it run, store the big value in the PMEM, and store the SDS pointer in DRAM itself, right? And for int, for embedded string, that's normally the smaller data size according to the encoding principle. So we'll still keep that in the DRAM. And secondly, which is the list type. List type is a little bit more comprehensive. It consists of the quick list data type, right? The quick list has the quick list node, which includes the zip list in the behind, while the zip list might have more than the threshold I mentioned about just now. So most of the zip list will be stored in the PMEM. Okay, and this is about hash as well. Hash has two implementation encoding. One is the zip list, one is the hash table. Right, the zip list, we also similar like what we have did before, store that in the PMEM, keep the pointer in the and data management structure in the DRAM itself, while keep the large value there in the PMEM, and similar to hash table. This is the set, right? The int set and hash table similar, since intercept will be or small int value, it should be very smaller than the threshold I just mentioned about. Keep that in the PMEM due to there's typo there maybe. Keep that in DRAM due to small size, and keep the rest of the hash table in the PMEM. Right. This is the last data type I mentioned about. Go ahead.
So all these segmentation or changes, are you expecting the software developer of the application to do it, or somewhere at the Redis layer, like Redis Lab would be helping?
Right. So we are engaging with. That's right. I know.
Basically asking for changes to the application.
That's right. That's right. So this is what we want to achieve the best performance on the persistent memory. So we modified the data type one by one, right? It has to be a lot of the disruptive change on the code itself. That's true. But we're just showing what the best performance we can gain from there, right? From this kind of the threshold setting or the data mem placement strategy. But as you said, to make it more public or scaling out to more user, we're talking to we're planning talking about the Redis Lab to see how they accept this approach. But by the way, similar to PMMIO, there's Redis POC to see how to leverage the PMDK as the prototype. This kind of work is already also put in GitHub, open source to everyone, right? So when you get the device, probably you can try that by yourself. So it should be very comprehensive, easy to run, and also we validate that in our internal side. All right, the last one, the Z-set, similar concept as I introduced before, which I won't go through that detail. So talking about the second scenario, which is more interesting about the persistency one, right? Use the PMEM to improve the performance of the Redis persistency, which is the also very interesting one that almost everyone, not every scenario, but the keep data durability and persistent is the big requirement for the end user itself, right? So how we use that to improve? Simple way, right? If you know PMDK, you should know there's the libpmem obj, this kind of the function can directly be used for the data persistency to the PMEM. But this is also the second, first gut feeling we should use that, right? We put everything in the PMEM, so it will be persistent by default, right? If we have the persistency, enabled there. And secondly, just to mention about the libpmem obj to store all data in the management structure there is what we do. And so in this case, the AOF or RBD should not be the mechanism to keep its persistency, but the PMMDK itself should do that, right? And so it has some benefits. Like it doesn't need to store like AOF file or RBD file anymore. It can save the large disk space to, spare that, right? And it can provide a fast, data store after server reboots. Because the data is already there. It doesn't need to restore from the file, from the disk there, right? So and this is what has been already been there in the GitHub on PMMIO website. But second one, when we take about into see how we improve that performance, right? By the way, the performance of previous one is not that good from our perspective yet. We can better improve that. So we introduced one concept called pointer-based AOF, right? The pointer bit to the AOF, how that can be, right? So this is considered about the Redis has the mechanism to persistency itself. How to leverage this kind of the workload, which can keep persistent data itself, right? So we, simply to say, we store the keys in the DDR and the AOF as well, right? And store the value in the PMEM, just keeping the store the pointer to AOF, just keep the pointer to the value in AOF as well for the recovery. So it will still continue to inherit from original AOF mechanism, but leverage the PMEM to store the big value and higher performance of the device, right? So jumping to the performance, result itself is much better than what we have seen in the previous option one. First, and also that depends on how the sync interval that's set to be, right? If the AOF sync interval is set to always, means every operation it will track in the real time to keep that in the AOF file. But if you treat that the sync as every second or every minute, the performance delta may be different. But this is what I talk about, the best performance we can get on keep the sync in always case, right? And there's the URL, you can see the code. This is the illustration how the mechanism looks like, right? You see in the left picture, it's original what the current today Redis has for the AOF relationship to different kind of device. It has the keys and values stored in DRAM, right? Every operation it has the AOF file store what the key value is supposed to be, right? And so in step one, in the right picture, it shows how we modified today, right? Mapping to different steps. When the step one, there's a write request from the client side. When the server requests that, it will store the keys in the DDR, just like we mentioned before, right? And it will store the values in the PMEM to keep the large value in the PMEM itself. And then still keeping the AOF file, but just keeping the very minimal, value address in the AOF file. So the AOF file compared to the previous one is quite small, right? It doesn't store the real value, but just store the point address of the PMEM value there. So with this way, the disk there is no longer the bottleneck, right? It can be less than the previous case should be the bottleneck in AOF file write, but it will improve better performance for overall persistence and mechanism, right? So just like mentioned there, the data management philosophy is to store the key and the value pointer in the disk, right? Not the value itself, to improve the PMEM bandwidth utilization efficiency. That's the way we want to better utilize the PMEM. Sure.
There's a crash between steps 3 and 4, so do you have some memory leak there?
You're saying memory leak?
Yeah, so what happens like if you store the value in the PMEM, but you haven't stored the key in AOF, and so there's a crash between 3 and 4.
That's very,
keep on crashing,
sure.
Are you going to accumulate
That's a very good question, actually. For the time zero, I didn't put that kind of implementation here. But additionally, we provide one mechanism here, like 3 to 4, like the redo log, undo log leaks kind of the mechanism. We call that our persistent ring buffers, this kind of the implementation, right? With that, there's log record itself in the. By the way, the persistent ring buffer we're putting in the PMEM itself as well, so it will track whatever the crash may be happen there, right? And revert back if the data can have the issue. Sure.
I'm guessing generally the AOF is protected somehow with RAID.
Mm-hmm. Right.
But now it points to the PMEM. Would you sort of create multiple PMs or?
We didn't put consider about the situation. Put the AOF file in the RAID itself. This is still within one server, right?
Right, but even within one server, generally one would want to protect against single device failure.
Right.
And maybe the PMEM is more reliable than.
Okay. Yeah, that probably belongs to how we keep the high availability or the ability for PMEM itself, right? We haven't considered that case in this kind of implementation. There's the RAS feature you can be aware in the PMEM products, right? It's supposed to be those kind of the features guarantee the high availability of the PMEM itself, right? All right, and after the introduction of the previous scenarios in data management strategy, to make it more complete, right? We're not going to just to build a POC or prototype to be that. We're really serving the end user who's going to use that in production environment. So we checked on what's missing there in the current implementation. So there are two actually. One is the data retirement support in the after Redis 4.0, and the other was the data defragmentation, which is also supporting after Redis 4.0. Right? Consider adding the PMEM itself. It needs to consider how these two needs to be supported, and also the other interesting pitfall was the Linux copy and write mechanism. It's not supported there by the in today's kernel, right? So to support complete features in the Redis itself, we cover the data retirement support, which is the RRU support mechanism. The implementation can be very simple. Just to add the PMEM device into the consideration itself, to say either DDR or PM, has the space. The data, can be moved around, right? If there's DRAM, there's the traditional ARRU only supports the DDR4, but when we add the PMEM, we should consider those two as the holistic, memory space, which will kick the value or keys from DDR to PMEM until they are both full. Right? So this is the support how to evict object in the PMEM needs to be added to be make the holistic feature support there. And second one was the defragmentation as well. So Redis 4.0, it has the JMalloc to support defragmentation. But it needs to be additional, leverage the JMalloc, which used by libmemki to support defragmentation space in PMEM as well, right? The mechanism how to do the defragmentation leverage the existing Redis logic to say put every object in the checker function and then decide whether this kind of the data should be retired or not. Or not retired, the move around to be more defragment, right? To less defragment. So that's the point. And this is the pitfall introduced to Linux copy and write, which is very common scenario when we did the if we want to put the Redis into a cluster, right, or use the RBD feature of the Redis, it will make the data dump there. All right, if there's cluster this server needs to replicate to that server. This kind of feature needs to be supported by Linux COW. Means when it needs to perform a dump option, it spawns a child process. In the DRAM, it's okay, right? The child process can have the separate, process domain. But in the, persistent memory, it's different. The current kernel is not supporting the, child process to see different, space yet. So when there conducts a fork function, the child process will see the exactly same memory space like the parent did. If at that time child process is going to dump the data, and the parent process is to receive a data modification or data update, then data corruption risk will happen, right? So this is the common pitfall we met, in the current implementation. So what can be mitigated, right? So have to think our mind to see what additional business logic can be added to be there. So we introduced two hash tables actually to keep the data as the temporary storage to store there. These two hash table, one is the new value table, and the other was the updated value table. So these two tables will help the parent process to decide whether the data needs to be duplicated, temporary stored in those, hash tables or not, right? And so with that kind of support, even they see the same, memory space, we still can keep the data, consistency between them. All right. So quick summary. What the Redis, can be do with Next-gen PMEM with this kind of work we do. We enable that with the full compatibility API as before, right? User can be less sensitive, changeable on their core how they use the Redis. It's compatible with the open source 4.0 plus, and it has higher capacity per instance, which means the lower TCO the cloud service provider providing those kind of service can be, right? And the way you use the PMEM, it is used more like the volatile device, right? So it can have the larger capacity support to that. And for persistency demands, if there's any, just using the mechanism I mentioned before to help the high performance persistent, comparing to previous one, it can up to like several x to previous what the the Redis on the AOF file needs to be. Also depends on what the interval is set to be the transactional persistency, right? So this is the reference where you can find the resource there. The PMDK is always what we want to recommend to, right? We use the lib PMEM generally in the background in the very layer. So we didn't use lib PMEM OBJ as we mentioned before, but lib PMEM is used to have a very good reference to adopt. And memcnd, lib memcnd is the one we just treat that as the malloc, using in the persistent memory. These two are very common to use and easy to use there. And the second one is the what you want. If you want to really familiar with what Redis and Redis Lab do, go to the redis.io, can get that information. And the last one is the the version we put that. You can download and check it out what the code changed that to be, and download by yourself to try that, right? So that's pretty much for the day. Any more question? Go ahead. You are saying in those two scenarios, or I think those two scenarios, one they're actually mapping to different use cases, right? The first one is more mapping to what the basic volatile can do, right? And the second one is mapping to what the persistency user needs to have, which has the penalty to store data, still store data either in the PMEM or in the traditional disk. Right? So if you only look at the performance, definitely the first one can be better because it doesn't have any penalty to have the persistency demands. But in each one of them, I comparing option 1 and option 2. The ones with better data management to be aware of what the data it has in the application has the better performance. So that's the general answer to that. All right, go ahead. Oh, okay. Yeah, I'm not sure whether we have the those developers as well, but the one we're putting the PMEM.io, which is the early two, you can see that, right? It's the one leveraged best in the how to illustrate how the PMDK can be used, right? Just like to say the PMEM OBJ how it needs to be added. It doesn't need to RBD or AOF file anymore. That's the traditional how the other application can be modified to, right? But this one we just highly customize according to data management policy itself, and collect the real user feedback to make it more production adoption usage there.
So you mentioned 4 design options. Does this one implement all the 4 in
Yeah, the previous option by the way, that's not 4 design options. That's just option 1 and option 2, right?
2 for each.
Yeah, right. Implement. This one has the option 2 in 2 scenarios.
This one does not implement the volatile case.
It does. I mean, the option 2 in the volatile case and option 2 in the persistent case, right? Yep.
So regarding the copy on write problem, do you have any insights into how it could be solved within?
Oh, yes. Yeah, this is also interesting us there. Our kernel team, has a lot of discussion to see how this is supposed to be supported, right? I don't have that kind of detail in today's source there. Probably can, if you want to know about that, I can put in the offline information to see how their community discussion today is. But so far, we didn't see clear timeline when the community is going to support that. That's the reality it has to face right now.
Well, I was thinking that if the PMEM-aware file systems like ext4 or XFS could have essentially support for snapshots.
Yeah. Right.
File level.
It needs to be supported as well, to have the copy and write. If you want to code about the sophisticated file system, I think it has to be support the copy and write there, right? But today but this is not using the file system there, right? We didn't try that approach to evaluate that detail. Yeah.
So you mentioned for the copy and write, you have 2 hash tables.
Right.
Once you're done with the copy and once you're done with the snapshot, are you going to merge it with these 2 hash tables?
It will be deprecated, if the dump was finished there, right? The child process is gone. It doesn't need to keep there.
I thought one table is with old data, another table with the new.
Oh, okay. It's not that way. It's not to have all data to copy into one hash table. It only records when the data was changed in the parent process, right? Either data was new added, it will add it into the new hash table, right? Or is there any data is updated? Just that data was stored in the change to the updated hash table.
Yeah. So basically, you have one hash table that has a new data.
Right.
The data gets modified.
Right.
And then another
Oh,
table.
that's not right. That's the original data into the into the hash table, not the new data. The new data was already modified on the parent process there.
I see. So the child is
Right. Exactly. Yes. Yep. That's it for today. Thank you.